last session before the break. We're on time, so you got to do good. The last talk before the break is by Dai-Nam from the University of South Florida. We'll be talking about Landau.
This meeting is being recorded.
Landau-Zener tunneling the Dissipative Systems quantum state split nanofriction.
Thank you, Dr. Joe, for that introduction. So, my name is Dai-Nam. I'm from the University of South Florida, and today I'm talking about our research about Landau-Zener tunneling in the dissipative system and the case of the quantum stick clip nanofriction. So this is the work between me and Professor Landau-Zener. And yesterday she already performed a talk about the friction problem with the machine learning. But in her case, she focused on the static friction, and today I'm talking about the dynamic friction. So here I want to shout out a little bit about our research group as a University of South Florida. So our mentor is Professor Landau-Zener. She is associate chair of the Department of Physics of University of South Florida. We have two postdocs, me and Dr. Moby. And we have currently we have two PhD students. And our research is focused on 2D material, something related to light matter interaction, 2D materials such as like Gaussian physics. Whenever interaction, we try to develop some different methods to tackle some problem in calculating whenever interaction in material. Like recently we developed a pocket which including the localization of the like binarialization of the wave functions into the whenever interaction, or we also try to include some non-linearities optical response in especially in whenever interaction. We're also looking at some problem related to energies transport like thermoelectric or heat transfer radiation in material, especially in 2D material. One of our spin-off research is related to spintronic in TMDC. So this is like our spin-off cooperate with the experimental groups in our university. So we are always willing to collaborate with all of the research group around the world. So about my talks, I'm considering the dynamical frictions. So unlike the static friction, where we move two materials together with a very extremely slow velocity, now I consider a more realistic problem where when we have the non-zero velocity of bracket between two materials or between one atom and a material. So most of the time, most of the common way to solve this problem is considered in classical mechanics. So like there's two typical classical model. One is called Landau-Tomlinson model, where we consider the 1D chains of atom as a base material, and then we move one atom around above that chain of material. So in the original research, the moving is based on the AFM tip. So we have a cantilever level, and we wrap the our atom along in front of the 1D material. But Recently we find out that we can also use the optical tool like optical crystal as a to write the atom instead of the AMF. So the benefit of the optical crystal is that we can change the spring constant by changing the shape of the optical crystal effective potential. Another model is considering one-dimensional chains of atoms wrapping together. So this is more like a generalized of the previous model, where we consider the sliding object is now the another 1D chains of atom. And in this case, in this model, they can also consider the incommensurate or commensurate structure and other like effect like this location effect, phonon effect, and other things. But we focus more on the first model, Brandon-Tomlinson model. In that model, there is a factor is called corrugation coefficient eta. This is purely classical parameters, and it tells us how many minima, how many local minima in the potential surface that our particle will experience. And such kinds of local minima, the number of local minima, it tells us how many slip motion could happen in our in the classical motion. So for example, if this eta is less than 1, there is no friction. It's just simply the like the ion or the particle is just moving along with the optical track or with the harmonic track. But if there is like 2 local minima, 3 local minima, then we will experience something like stick line in the first half of period of time, and then following up by the sleeping motion. And I will show later in my study. And even that in this model, they only consider one atom moving along one-dimensional chain of atoms. This model can also apply in the case that when we have two material, like in this study, they consider like M2 MOS2 layer, and we can consider like inside the material they have the stick lip interaction is similar to this model, and then we can use some kind of some known result for the Brandon-Tomlinson model, and then we interact. We can find out the interaction energies in this model. So here is our model that we consider the to write our item by the optical crystal. So we have 1D chains of atom. They separate by a distance a. So it will create a periodic potential with the height of U0, and then separate from that chain of atom, we have our target atom, or maybe in realistic, they often use the ion. So ion is easier to control, to track by optical crystal than the neutral atom. And this atom, it could be separate. We can control its position by the distance d. So it's very important, because if this if we change the distance d here, we will change the height of this periodic potential, and because in that if d is very large, the dominant interaction between this atom and the chain is a fundamental interaction. But if we bring that atom close to the chain, it will interact by different mechanism. It's based on like the overlap of the wave function of electron in this 1D chain and in this atom. So we try to write this atom with the optical crystal that characterized by a frequency omega, and the center of the track will be frequent by a velocity v. So the total potential surface that the atom will experience is this red line. And we can easily right now is Hamiltonian of the system, which is just the one body Hamiltonian in one dimensional space. So here I just show in the dimensionless unit. So so the first thing we want to looking on is what we're looking at is the quasi-static eigenstate of the Hamiltonian. So let me recall that our Hamiltonian is time dependent, and the time dependent is because the optical trap, removing the optical trap. So the center of the optical trap is this one. It is time dependent. So to solve it, we need to choose a basic set. So normally when people try to solve the Schrodinger equation, they often try to choose a time-independent basic set of wave functions. But we find out that because the harmonic potential, which is a parabolic shape, so it's always dominant in a very large distance compared to the periodic potential, because the periodic potential is only have a finite height. So in that case, we choose the basic set of the harmonic oscillator instead, although that basic set is time dependent. In this case, we can easily present our Hamiltonian as this matrix, which is time dependent. And the quasi-static eigenstate of the system we can obtain by diagonalize our Hamiltonian, where the time is just a parameter. So this is very important because when we consider the dynamical evolution of the of this Hamiltonian, then we consider time is time. Here we just consider time is simply a free parameter.
So your basis set at time t and t plus delta t
It will be different.
are not orthogonal.
Yeah.
So how do you deal with the overlap?
Yeah. When we solve the quasi-static eigenstate, then the time t and t plus delta t will be independent. But in the dynamic code, we will have the overlap matrix. And in our case, we're lucky that because harmonic oscillator eigenstate is just expressed in terms of some classical, classical polynomial. So all the integral is known, and we can easily obtain everything analytically. Yeah. So I'll show you later in the next slide, next few slides.
Yeah. Less than a minute.
Yeah. So for example, if we choose some set of parameters like this, we are able to solve the first pi eigenstate as a function of time. So it's noted that because we have the periodic potential, so in terms of time, it's also periodic in time t, capital T here. And we in this case, we show here that at some point of time, we will have some kind of anti-crossing when the two levels is close together. It looks like they try to cross together. So in terms of the transition, we know that when we have the anti-crossing like this, as some if we can solve the Schrodinger equation, time-dependent Schrodinger equation, at some moment we can have some kind of like diabatic transition, and the result is known as the Landau-Zener formula. So that's why I show it here. In some case, we will not experience something like this. And the reason is because when we're looking at the matrix element of the potential, we see something that like, because we have some term like this, which is inverse proportional to the atomic distance in the 1D chain. So if this parameter is very large, then when this parameter is very large, then the exponential term here is go to 0, and we experience something like there is no contribution from the periodic potential at all, and this can be understood because easily understood because now our 1D chain, the atom is very close to each other, so it looks like a continuous, and there's nothing contribute to the shape of the potential surface. in the other limit, if the 1D change, the interatomic is very large, distance very large, in that case, then this factor is go all the way down to zero very fast. Yeah. And we also experience something like the potential, the periodic potential is only right move up and down the energy level like this, but it does not change the gap between the level. So the spacing between them is the same. It's the same as the first case. In these two limits, we never observe something like anti-crossing. But we see we find out that if this ratio is comparable to unit and our classical configuration parameter is larger than 1, in this special case, we can have the anti-crossing between level. And if this eta is large, it increase, then the chance that we have more and more anti-crossing. And this is, we can explain.
The thing is from forward now, Dai? This is
Yeah.
break now, yeah?
Yeah.
Sorry.
Yeah, I'm sorry. So I'll try to move faster.
I mean, it's over,
So-
we have to stop now, because it's the break time.
Really? It's
Yeah.
15 minutes?
Yeah, sorry, so we have to stop now. I mean, you can say one more thing if you want to stop, you just go to conclusion. Yeah, just the
Yeah,
conclusion.
I'll jump to the conclusion. Maybe. So this is dynamical. This is the dynamical equation that you asked. Here the overlap, and we can obtain it analytically. I have to show it the result here. But for example, if we have the velocity, if we move with a very small velocity, this is the quantum energies, and it looks like adiabatic theorem. But when we increase the velocity, then we at some moment, some velocity, we will have some because of the Landau-Zener tunneling. Our particle can stay in the higher state instead of the ground state. And we expand our model by including the role of the environment. In this case, you can see in this case, we will have something like, because of the environment, then if we have the tunneling, then the particle will stay in the higher state and it can release the heat to the environment. And that is experienced as a fiction.
Let's take that.
Yeah.
If you have any questions, you can go to the break. I think we're gonna go straight to the break now, because we want to keep the schedule for lunch, because I want you guys to get out there. I think 12:45 is going in, and I'll be able to start. So back here, we're back here at 10:45, yeah? So it's 10-minute break, sorry for that. And with Professor King,